Okay, so hello and welcome back. So the next question that we have is question number 5, which is, well, I have been going through these questions. These questions are not that, are some type of, not really that challenging, really. Some of them are, well, let's go through them one by one. Let's see what we have. So question number 5, we have basically show that the function f from r to r, show that this function from fr to r given by f of x is equal to x raised to the power 3 is injective. So if you want to show that this function is injective, that means that you want to show that f is basically 1, 1, right? Which means that if you basically you can suppose that, for example, suppose that some f of some x, for example, is equal to f of y, where basically x and y belong to R. Now f of x is equal to f of y, that means basically if f of x would be x cubed and f of y would be y cubed, right? Now we need to show that x is equal to y, right? We need to show that x is equal to y, because, and the reason why we need to show that is that we said that basically to show that the function is 1, 1, basically we said that if a function is 1, 1, if f of x1, for example, is equal to f of x2, implies that x1 is equal to x2 for every x1 and x2 belonging to, for example, belonging to the domain of the function, whatever that might be, or belonging to the let me take a look at the definition. Okay, so the exact definition is basically this. The exact definition is a function f, a function f from x to y. A function f from x to y is defined to be 1, 1, is defined to be 1, 1, or injective if the images of distinct elements of x under f are distinct. If the images of distinct elements of x under f are distinct, are distinct. That is, for every x1, x2 belonging to x, f of x1 is equal to f of x2, implies that basically x1 is equal to x2. Otherwise it's called many 1, right? So so that is basically the definition. And so you can imagine that you can assume that, for example, some f of x1 is equal to some f of x2 for some x1 and x2 belonging to the domain of the function. And then you need to show that basically this implies that x1 is equal to x2. So for the same reason here we did the same thing. We suppose that f of x is equal to f of y, where x and y belong to R, which is the domain of the function. And now we need to show that basically, and f of x is equal to f of y means that x cubed is equal to y cubed. And now we need to show that x is equal to y, right? And of course it's easy to show that because when you have x cubed is equal to y cubed, that means that basically if you take the cube root of both sides of this equation, you get the cube root of x cubed is equal to the cube root of y cubed, which means that x is equal to y. And so you can conclude that basically f is 1, 1 or injective. Now the way that they have solved this problem in the solutions is that they have said that they have come all the way up to this step in the exact same way, but they have not solved it this way. Meaning that what they have said is that now we need to show that to show that basically x is equal to y. Suppose that, and then they have used some sort of contradiction. So suppose that x is not equal to y. Their cubes will also not be equal. And so their cubes will not be equal, which implies that x cubed is not equal to y cubed, right? But here we said that x cubed is actually equal to y cubed. So this is a contradiction. And therefore what we assumed here was wrong, meaning that the assumption that we made was actually not true, meaning that this is false. So basically the logical opposite of this is going to be true, which means that x is equal to y. And therefore f is injective. Right, so that is basically question number 5. Okay, so that was question number 5. Now question number 6 is give examples of two functions. Give examples of two functions f as a function from n to z and g as a function from z to z, such that g of f is injective. G of f is injective, but g is not injective. Right, so that is the question. And as a hint, we have consider f of x is equal to x, and g of x is equal to the absolute value of x. That is the hint that you have. So what you need, but this question doesn't make much sense, because they have already given you the answer, meaning that, for example, here, if I say that, for example, f goes from 1 to n to z, for example, and if I define g as z to z, for example, then of course this is not going to be 1, 1, right? But then n to z, meaning that GOF would be, GOF is the same thing as g of f of x, which is the same thing as, well, the absolute value of x, and GOF would be a function from n to z. GOF would be a function from n to z. And n to z. Well, of course, this function is injective, because normally the absolute value of x is a function like this. Basically, you have these two lines over here, right? But since the domain of your function is n, then this part of the function is just simply not relevant anymore, and so the function becomes injective, right? So that is basically, that is the shape of your function, and the function becomes injective. Otherwise, g itself is a function from z to z. G itself is a function from z to z, and you know that z is basically all of these numbers, and all of these numbers, of course, only the integers. And g is basically, g of x is equal to the absolute value of x, meaning that you have basically a function like this, both the parts of the function, and your domain is this all of these integers, negative and positive and 0, and your range is all of these integers. And of course, you can see that, for example, this output it can be mapped to this point and to this point of the function, meaning that these 2 points have the same output, but the inputs are not the same. This is the input for this output, this is the input for this output. Meaning that if I call this, for example, f of x1, and if I can call it also f of x2, for example, for the sake of argument, and you can see that, and call this, for example, x1 and x2, so this becomes f of x2, for example, and this becomes f of this, and this becomes f of x1. So you can see that f of x1 is equal to f of x2, and x1 is not equal to x2, and therefore g is not 1, 1. But since in this case the function has only one of these parts related, I mean, there is only this part related to the function, the other part of the function is practically not there, because you're working with a set of natural numbers, and the natural numbers start from, actually they start from 1, meaning that the function is actually defined from here, if you take this as 1. So that problem doesn't simply arise. It's a good question, actually. I hadn't actually thought about it that way. And so, in order to solve the problem, let's solve it the way that they have solved it in the solutions, because this is just some discussion, and we need to write it down also in a logical way. Okay, so as the solution here, we have basically defined f as a function from n to z, as basically f of x is equal to x also define g as a function from z to z as g of x is equal to the absolute value of x, right? And first we need to show that, but since the question is asking g is not injective, first we need to show that g is not injective. That g is not injective. And in order to show that, we have g is a function from z to z as g of x is equal to the absolute value of x. So g is a function from z to z and g of x is equal to the absolute value of x. Now let's suppose that for example g of x is equal to g of y for some x and y belonging to the set of integers, the domain of the function. And what that means is that the absolute value of x is equal to the absolute value of y. Now here you have basically here you have a couple of here we have a couple of basically cases. But what you can do is that you can basically use a counter example that would be easier. Basically this function is simply this function here, and this function is basically a function like this, and of course by looking at the function you know that it's not injective. But in order to show that, you could argue that, for example, you could for example take a 1 over here and negative 1 over here, and you know that, for example, g of 1 is equal to the absolute value of 1, which is equal to 1, and g of negative 1 is equal to the absolute value of negative 1, which is equal to 1, which means that g of 1 is equal to g of negative 1, which is equal to 1, and 1 is not equal to negative 1, and therefore g is not injective. G is not injective, right? Now, the next part of this question, you need to show that basically g of f is actually injective. So g of f is a function from f to g of f is basically a function from n to z. G of f is a function from n to z, and g of f is the same thing as g of f of x. Now g over here we have the absolute value of x, and f of x is equal to x, so g of f of x becomes again the same thing, the absolute value of x. So g of f of x is equal to the absolute value of x. Now the domain of this function is the set of natural numbers, and of course you can argue that for example, let x and y belong to n such that such that GOF of x is equal to GOF of y, such that GOF of x is equal to GOF of y. So you have basically GOF of x is equal to GOF of y, and x and y belong to the set of natural numbers to the domain of the function, right? Which means that basically the absolute value of x is equal to the absolute value of y, which means that now since both x and y belong to the set of natural numbers and both are positive, and therefore the absolute value of x is equal to the absolute value of y implies that x is equal to y. Hence, and you can say that hence GOF is injective. Right? So that is how you write this down logically, but of course I find that the way that I explain those examples, at least for me, is a good way to understand the problem, but well, of course you do need to write down your solution in a logical manner as well. That is also important, very important, of course. So that was question number 6. Question number 7. Question number 7 is give examples of two functions. Give examples of two functions f as a function from n to n and g as a function from n to n, such that GOF is onto, but f is not onto. So, as a hint, we have consider f of x is equal to x plus 1 and g of x is equal to x minus 1 if x is greater than 1, and it's equal to 1 if x is equal to 1. So that is the question. Now, so you want to give examples of two functions f and g, both from n to n, such that GOF is onto, but f is not onto. So, of course, we did have this in some part of the theory that we had in this chapter, this concept. So, of course, f is a function from n to n, and you can imagine that f is this function here. F of x is equal to x plus 1 would be basically this function here. So this is f of x is equal to x plus 1, meaning that basically what happens here is that your domain is the set of natural numbers and your codomain is the set of natural numbers, meaning that actually this part of the function is actually not a part of the function, right? Because your domain is the set of natural numbers. Now, now you see all of these values. If you go for x plus 1, so if you go for example, every x is mapped to x plus 1. Meaning that if I write, for example, if f of x is equal to x plus 1, if I write this as y is equal to x plus 1, of course there is basically, there is we don't have any problems here because the set of natural numbers actually starts with a 1, so all of the values here are not a problem. Before 1 all the way up to 0, that's not a problem. But if I write y is equal to x plus 1 and x is equal to y minus 1, then that means that f of y minus 1 is equal to y. That means that any y that I find in the codomain of this function, in the codomain which is n, there has to be some y minus 1 that is mapped to that. So if I start from, for example, 1, if y is equal to 1, then y minus 1 has to be equal to basically 1 minus 1 is equal to 0. So you see that basically y is equal to 1 is actually not, I think basically the graph has a problem. This is not the right graph, most probably. Because if I do the graph here, what I will find is that f of x is equal to x plus 1, and then the graph is actually right. So the graph, as you can see, goes from, this is 0.0, 1, but what I'm saying is that, right, so as you can see, this point, exactly this point, which is y is equal to 1, the problem is that this x is equal to 0 is not in the domain of the function, right? Which means that the function is actually not onto. You see over here, y minus 1 is equal to 0, which does not belong to the set of natural numbers, and therefore you can say that f is not onto. I hope that you understood what I meant by this. Let me do this. Let me basically explain this again. So let me just simply erase all of this. And this function over here, f as a function from n to n, which is f as a function from n to n, defined by f of x is equal to x plus 1, this function is not onto because you can see over here this point over here, which is basically y is equal to 1. It is actually a part of the codomain of the function. The codomain of the function starts from 1 2, 3, and so on and so forth, right? Now, if you take a look at this point is actually 0, 1. That means that the x-coordinate of this point is 0. And the problem is that 0 does not belong to the set of natural numbers. And so the function, so this point has a problem, meaning that this point has not actually been mapped to anything, which means that or is not the image of any element in the domain of the function, which means that the function is not onto. What you can do alternatively to decide this, to understand that f is not onto, is that you can write f of x as x plus 1, and you can say that let us, for example, take y as an arbitrary element of the codomain or n of f, and therefore you can write, instead of f of x is equal to x plus 1, you can write y is equal to x plus 1. And if I calculate x in terms of y, I'll get x is equal to y minus 1. X is equal to y minus 1. And what that means is that then f of basically y minus 1 is going to give me y, because, well, here I'm saying that f of x is equal to x plus 1. And since x is equal to y minus 1, then f of y minus 1 is going to be equal to x, which is y minus 1, plus 1, which is equal to y. So f of y minus 1 is equal to y. That means that any f that I find in the codomain of this function, if I want to get to every y that I find in the codomain of this function, if I want to get to that y, I need a y minus 1 in the domain of the function, right? Now the problem here is that, for example, 1 belongs to the codomain of this function. 1 belongs to basically n, the codomain of f. The codomain of f. The codomain of f, right? Now, in order for 1 to be an image of some element in the domain of the function, since y is equal to 1, then y minus 1, which is the same thing as 1 minus 1, which is equal to 0, has to exist in the domain of the function, which is not the case. As 0 does not belong to the set of natural numbers, and you see that the domain of the function is the set of natural numbers here, and therefore f is not onto, right? Therefore f is not onto. Now, basically GOF, in the same example, GOF is is basically to define GOF. Basically to define GOF, so GOF is onto, but F is not onto. So now in order to define GOF, we have, so GOF is going to be some function from n to n, of course, right? So GOF is a function from n to n. And the rule of this function is going to be as follows. Okay, so now to define the function GOF, what you need to do is that basically, first of all, G is the same thing as, let me write down the function G. G is a function from n to n, if I'm not mistaken. Yes, and it is x minus 1 and 1. So G is G of x is equal to basically x minus 1 and 1 if x is for basically for x is equal to 1, for x greater than 1, for x is equal to 1 and x greater than 1. So, and f is the same thing as, and f is the same thing as f of x is equal to x plus 1. And f is the same thing as f of x is equal to x plus 1, and it is a function also from n to n, right? So that means that GOF, you can write it as GOF is the same thing as G of f of x. Now, well, you need to basically, first of all, in this clause of the function, you don't have any variables here, right? So that means that G of x is simply equal to 1 when x is equal to 1. So when x is equal to 1, then G of x is equal to 1, and which means that it does take care of the problem of 1 for us. It does take care of the problem of 1 for us, which means that if I want to create G of f of x, I have to write it as x plus 1. So then G of f of x becomes basically let me take a look at this function. Okay, so now in order to understand how to compose these two functions, we need to take a look at the functions themselves, basically an arrow diagram of the functions, right? So so basically in order to do so, so basically we have f and g. F is defined from n to n. G is defined from n to n, meaning that, for example, let's say that you have the set of natural numbers here, and the set of natural numbers here, and the set of natural numbers here, right? So this function f, what it's doing is that every input that you give to this function, it's going to add 1 to it, and it's going to map that input to some output which is 1 higher than the input. Meaning that suppose that you have 1, 2, 3, 4, and so on and so forth, all the way up to infinity in the set of natural numbers. And you have 1, 2, 3, 4, 5, and so on and so forth in the set of natural numbers. And you have 1, 2, 3, 4, and so on and so forth in the set of natural numbers. If I assume that f is a function that goes from this set to this set, so every input is mapped to some output which is one higher than that input, meaning that you will have basically some 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 4, 4 is mapped to 5, and so on and so forth. And so you can see that 1 is not mapped to from any of these elements here, and so you can say that f is not onto, right? Now let's say that g is a function that goes from this set to this set. And what g does is that it says that whenever you give me an x, I'm going to give you an x, meaning that I map 1 to 1. So 1 is mapped to 1 here. And whatever input you give me, I'm going to give you an output 1 less than the input, meaning that 2 is mapped to 1, 3 is mapped to 2, 4 is mapped to 3, 5 is mapped to 4, and so on and so forth. So you can see that f is actually onto, meaning that all of the elements here will be covered. And as you can see, so GOF is a function that goes from basically this set to this set directly. This is GOF, which means that 1 is mapped to 1. So that means that GOF of 1 is equal to 1. GOF of 2 is equal to 2. GOF of 2 is equal to 2. GOF of 3 is equal to 3. GOF of 3 is equal to 3, and so on and so forth. That means that you could say that GOF of x is actually equal to x. And if you basically put these two functions together, you will actually see the same thing. Meaning that if I write basically, so this function has two clauses. This clause doesn't have any basically variables, so I'm going to have to use this clause in order to basically compose this function with this function. So that means that if I want to calculate GOF, which is the same thing as G of f of x, so if I want to use this clause, and the input of this function is a set of natural numbers, and here I'm saying that x is greater than 1, means that x has to be 2 here. After 1 in the set of natural numbers, you have a 2. So 2 is basically is given to me by this function. If n is equal to 1, then 1 plus 1 is equal to 2. So I can compose these functions together, meaning that the output of this function when n is equal to 1 is going to be equal to 2, which is the first input for this function, which means that I can write g of f of x, I can write, instead of x, I can write x plus 1, and then I have a minus 1 over here, and that gives me an x. And as you can see, GOF of x is actually equal to x. So that's basically how you put these two functions, compose these two functions together, and you can see that f is not onto, but FOG is actually onto. Now let's take a look at the solution here. Here we have so you already are hopefully familiar with the question. We wanted to give examples of two functions f and g, both from n to n. such that g of f is onto but f is not onto, and we considered f of x is equal to x plus 1, g of x is equal to this function that we are already familiar with. So this the solution based on the solutions that we have in the and of course you know that all of these solutions, I'm reading them from the Tiwari Academy. Let me show you basically the solutions here in case you want to have access to them yourself. So the solutions are basically you can go to tiwariacademy.com. They have good, I mean, all of the solutions related to these NCERT problems, all of the solutions that you can find on almost all of the websites that there are on the internet, all of the solutions are exactly the same. But on some of the websites, the way that they have been presented are actually better than the others, meaning that, for example, I found that on this website, Tiwari Academy, the solutions have been presented in a orderly, clean fashion, meaning that, for example, you can see that you have the question over here, you have the answer has been written properly in a clean language that usually doesn't contain any errors or anything. So I have so far I have had no problems with these solutions whatsoever, and I've been using them for the past 2-3 months every day, like 10 hours every day. I've been working with these solutions. So most probably you will run into no problems with these solutions. And so the solution is that, so you can define basically, you can define f as a function from n to n by f of x is equal to x plus 1, and you can also define g as a function from n to n by g of x is equal to basically x minus 1 for x is greater than 1 and for 1 for x is equal to 1. And we first show that g is not onto. We first show that g is not onto. And in order to do that, you can g is not onto. So in order to do that, of course, you see that 1 is mapped to 1 and g of x is equal to x minus 1. So you can see that actually you have to show that f is not onto. No, this is wrong. I was just saying that there is no mistakes here, but it seems that they have made a mistake in this solution. Actually, I was reading from the text. We are actually supposed to show that f is not onto, not g. G is actually onto. There is no problem with g. So we first need to show that f is not onto. So in order to do that, so we have already done that, but for this, consider element 1 in codomain n. Consider the element 1 in the codomain n. It's clear that this element is not an image of any of the elements in the domain n. It is clear that this element is not the image of any elements in the domain n, and so therefore f is not onto. And if you want to know why, we have already discussed this discuss this here, we can read this part, or you can rewind the video in order to know the exact reason and why that is. I showed you using the graph of the function and everything. And so f is not onto. F is not onto. Now GOF as a function from n to n is defined by GOF of x. GOF of x is equal to G of f of x is equal to G of x plus 1, G of x plus 1, which is equal to x plus 1 minus 1, which is equal to x. X belongs to n. Here, of course, x belongs to n, and therefore x belongs to n implies that x plus 1 is greater than 1. What this means is basically the same business that we discussed here, that because basically f of x over here is x plus 1, and then over here you have x is greater than 1, then you can put them together. And so what that means, then it's clear that then it is clear that for y belonging to n, there exists x is equal to y belonging to n. There exists x is equal to y belonging to n, such that GOF of x is equal to y. Hence GOF is onto. Hence GOF is onto, right? So that is the whole solution here, and hopefully you understand it, because we have already talked enough about this exercise. But and of course it was an important exercise, and we learned a whole lot of things on this one. Now the next question that we have is question number 8. Let's see, but before basically we will discuss question number 8 in the next video. I'll see you in the next video, and thank you.